Today's video will explain how the different levels of algorithmic efficiency affect application performance. Hello, I'm James Helfrich. Algorithmic efficiency is a measure of how an algorithm performs in relation to the size of the input. And this really is the best metric for efficiency of an algorithm because it's independent of the CPU performance, the other applications running, or other external factors which have nothing to do with the program itself. This video will discuss the different levels of algorithmic efficiency and see how they impact performance in the real world. Recall that algorithmic efficiency is how algorithm execution time is related to input size. And we have several different notations. The first one is O sub 1. The second one is log n. The third is linear. The fourth is n log n. The fifth one is n squared. And the last one is 2 to the n. So let's take a look at each one of these in turn. The first one is constant. Performance is unrelated to the amount of input into the algorithm. If I have 5 elements or 1,000 elements, it will take the same amount of time. The second one is logarithmic. The performance is a log of the amount of input into the algorithm. If I double the input size, it will take 1 extra unit of time to execute. The next is linear. Performance is directly related to the amount of input into the algorithm. If I double the input, it'll take twice as long. The next is n log n. Performance is linear times logarithmic. If I double the input size, it'll take twice as long plus 1. The next is n squared. Performance is a square of the amount of input into the algorithm. If I double the input size, it'll take 4 times as long. And the last one is 2 to the n. Performance is really bad. If I increase the input size by 1, it'll take twice as long. A lot of people have difficulty understanding how important algorithmic efficiency is. So let's take a look at an example. Let's say a single operation takes 0.1 second, or a blink of an eye. And there are 1,000 elements in my set. So once again, I'm going to have O sub 1, log n, and so on. Now, first of all, I'm going to take a look at O sub 1. That means the total execution time will take 0.1 second, even if there's 1,000 operations, because we only perform the operation exactly once. And this is faster than most people will notice. Really, it's instantaneous. Now, let's say it's log n. 2 to the 10 is 1,024, so therefore log n is approximately 10. So 10 times 0.1 second will be a 1 second overall execution time. And most people would notice a lag, but it wouldn't be a big deal. Most people would tolerate that. All right, let's say it's linear. Then 0.1 second times 1,000 operations will be 100 seconds, which is about a minute and a half. And it takes patience. Many users would give up and think it will not finish. They won't bother to see if it ever executes. Now for n log n, it'll take 14 minutes. Why 14 minutes? Well, the n part will be 100 seconds, and the log n will be to take 10 seconds. So this will be 1,000 seconds, otherwise known as 14 minutes. And most users would leave the computer and take a walk. Not many people would wait 14 minutes for something to finish. N squared would take a day. And most users would give up all hope. They would think it would never finish. 2 to the n takes 2 trillion times the age of the universe. It basically will never finish. Now, many may think this to be undesirable. However, if the algorithm necessary to guess a password takes that long, then it's desirable. In other words, some algorithms we don't want to finish. Clearly, each level is going to be much bigger amount of time than the one above it. What if it takes 0.2 seconds to perform an operation? And once again, there's 1,000 operations. In other words, it takes twice as long. How will that impact performance? Well, for constant, it'll take 0.2 seconds, which is, once again, faster than most people will notice. Log n will take 2 seconds, which is a noticeable lag, but still tolerable. Linear will take 3 minutes. And once again, it takes considerable patience. N log n will take a half an hour or 28 minutes. N squared will take 2 days, not 1 day, and 2 to the n will take 4 trillion times the age of the universe. So even though it takes twice as long, performance implications are pretty much identical, whether it takes 0.1 second or 0.2 seconds to perform each operation. What really makes a difference is my algorithmic efficiency, O sub 1, log n, n log n, and so on. We are willing to tolerate a great deal of cost per element in order to have slightly better level of efficiency. Algorithmic efficiency trumps everything when we're talking about a large number of operations. Here's another way to look at it. On the horizontal axis, I have the size of the input as n. On the vertical axis, I have a time in milliseconds. Now, first of all, we're going to do if it's O sub 1 or constant, in which case, then it doesn't matter how big the input size is, it's still going to take the same amount of time. Clearly, this is most desirable. Now, let's say it's log n. Initially, it's going to look linear, but then it's going to get flat. In fact, the larger the input size, the more log n resembles constant. If it's O sub n, then we're going to have a diagonal line. It's going to be straight. It's never going to get steeper, and it's never going to get less steep. If it's n log n, so for n log n, initially, it looks like a parabola. With every element, it gets progressively steeper. However, the steepness becomes constant as we get higher. For a very large value for n log n looks very much like linear. And the last one is n squared, and this looks basically like a parabola. We can learn more about algorithmic efficiency in the efficiency chapter of the software design textbook.